we'll work problem or 2 out of 11.7. We didn't get a chance to work many last class. So remember 11.7 is about optimization. So where we left off, we talked about a problem where we have a rectangle that we're trying to find the maximum area for. So let's suppose we call this distance x, this distance y. So we have that's x, that's y. Let's suppose we have 800 feet of fence with which to use. So if we're trying to close in a pasture that has 800, that is a rectangle, we have 2 of these, 2 of those, and if we want to make that pasture as large as possible, we're going to use all of our 800 feet of fence. Not going to have any left over. So that gives us how we can relate x and y. But what we're wanting to maximize is the area, not maxize. So the area of a rectangle is length times width. So length times width. But notice this has 2 inputs. We want to get this down to having 1 input where we'll have area as a function of 1 variable. So let's get rid of our y. We can solve for y in this equation and then replace y. So if we solve this for y, we would move the 2x over. So subtract 2x from both sides. And we can divide both sides by 2. So 800 divided by 2. 2x divided by 2. The 2's would cancel, leaving us 1x. So this relates x and y. If you tell me how long it is, I can tell you how wide it is. So we're replacing y with 400 minus x. So area, which is this distance times that distance, instead of calling it x times y, we can call it x times, this is 400 minus x. So notice we have 1 input now instead of 2. So area is a function of x. If we want to multiply that together, x times 400, x times minus x. So if we want to maximize that, remember if we have a maximum that occurs where our slope of our tangent is 0. So anytime we're looking for the slope of a tangent, we need our first derivative. The derivative of this term is 400. Bring the 2 down, x to the 1 less power, so the derivative of that term is 2x. So that's our first derivative. So we want to find out at what x value, at what x is our tangent line 0. So we set our slope, our derivative, equal to 0. Add 2x to both sides. Divide by 200, so we get our critical point is 200. So the x coordinate there is 200. Think about our input is x, our output is area. So if that's what's happening, we're not guaranteed that this is what's happening. We need to first of all show that we have a maximum, not a minimum, because there are also minimums when our slope is 0. So how do we show if this is a maximum or a minimum? We can do it using the first derivative test. If we know that the slope here is 0, we can check the slope on each side to see if we go from increasing, positive slope, to decreasing, negative slope. Or we can check what is the concavity. If it's concave down, if our bowl is upside down, then that critical point where we're concave down is a maximum. So let's do it that way. Let's take our second derivative. The derivative of this is 0 minus the derivative of this is 2. So if we substitute our critical point in, Notice our second derivative always equals -2. So at our critical point, we're concaved down. When our second derivative is negative, that's a concavity that's down. So if we're concave down at a critical point, yes, that is a maximum. So that just validifies that that really is a maximum, not a minimum. We want to know what the maximum area is. Now that we know what x gives us the max, we can substitute that into our function and say, well, when our x is 200, what is our area? So it'd be 400 times 200 minus 200 squared. So this would be 80,000. 1, 2, 3, 4. Yeah. 80,000 minus 40,000. So our maximum area is 40,000. When x is 200, our area is 40,000. If we wanted to know our dimensions, if x is 200, y is 400 minus 200, so y is 200, which we can check. Notice if we do length times width, 200 times 200, that again gives us 40,000. Remember, our length was in feet, so our area will be in square feet. So that's another example of getting the largest area possible. We can maximize our area function under the conditions we described. So let's do another one of those. Let's suppose that we have a sheet of paper, and on that sheet of paper, we're going to have an area where we could type, so forth. And let's suppose that in our area, we want to enclose, let's say, 50. Let's not do 50. Let's do 25 square inches inside there. So inside there, 25 square inches. So let's call this x and this y. So we don't know whether this is going to be long and narrow, whether it's going to be square. We don't exactly know yet. All we know is that this area in here needs to be 25 square inches. So when we multiply our x times our y, that needs to give us 25. Then we want to have margins of 1 inch. So this distance we want to be 1 inch. This distance we want to be 1 inch. This margin we want to be 1 inch. This margin we want to be 1 inch. So all the way around each margin we want to be 1 inch. So that means that on this side, if this is y, and this is 1, and this is 1, then we have y, and then 2 more. Y plus 1 more give us that total length, so y plus 2. For this, we have an x, a 1, and another 1, so if we add those 3 lengths together, we get the length horizontally. So we want to find out what do x and y need to be so that the area of this sheet of paper is a minimum. We want the smallest sheet of paper that has the required margins that we could fit 25 square inches on. So first of all, we need to figure out how do we calculate the area of the whole thing. Well, it's a rectangle, so length times width. So the area of the page is this full length times this full width. So length times width. But notice we have two inputs here. We have an X and a Y. We only want one input. So we listed earlier that X times Y gives us 25. So let's replace Y. Let's get rid of Y. So find out what Y corresponds to. So if we solve for Y, Y corresponds to 25 over X. So we can replace Y with 25 over X. So now this relates X to A. You tell me how wide this is, I can tell you the area of the whole thing. Tell me this distance and I'll give you the total area. Now let's distribute this, because remember, if we're trying to minimize our area, if we're trying to find the smallest area, think about our graph is going to have an input of X and output of area. So our graph might do different things. Might do something like this. We're looking for that point, the minimum point. So the minimum actually corresponds to an area. We want to find out what X coordinate gives us that area. What X coordinate gives us that area. So that's where our slope is 0. So if we're going to have find a slope, we need a derivative. So to get the derivative of this, we could use the product rule, or we could distribute first. If we distribute X times 25 over X, X times 2, this is 2 over 1 times that, so 2 times 25 over X, and then 2 times 2. So our area is 25, 4 more, so 29, plus 2X. And so that we don't have to use the quotient rule, let's call this 50 times X to the negative 1. So that relates X to A. So if we want to minimize that, if we want to find a minimum value, we need to get our critical points. So take our derivative. The derivative of a constant is 0. The derivative of that. Bring down the minus 1, so 50 times minus 1. X to the 1 less power. So our derivative is 2 minus 50 over X squared. Now that's undefined when X is 0. But notice if X is 0, we're not going to get any area in here. If this is 0, we can't get a square in here, or a rectangle. So the critical points we need to find are when our first derivative is 0. So let's add this to both sides. Let's multiply both sides by X squared. We can divide both sides by 2. Take the square root of both sides. Now, when we take the square root of both sides, normally we include plus or minus, but since X represents the length on this rectangle, we don't want a negative length. So the X, our critical point, is when x is 5. Our critical point is when x is 5. So let's verify whether or not an x value of 5 is a minimum like we drew, or whether it's a maximum. So we could either use the first derivative test or the second derivative test. Since we used the second derivative test on the last one, let's do the first derivative test on this one. So let's test the slope to the left of 5 and to the right of 5. So let's put in a test point of 4 and of 6. If we put in a 4 into our first derivative, 4 squared is 16. So if we do 2 minus 50 divided by 16, we get a negative. So if our first derivative is negative, that means we're decreasing. And then if we put a 6 in, 2 minus 50 over 6 squared. So we do 2 minus 50 divided by 36. We get a positive. So now we're increasing. So if at 5, if we go from decreasing to increasing, yes, that is a minimum. That's the minimum location of where we were looking. So in order for our paper to be as small as possible, x needs to be 5. If we want to find the area when x is 5, we can go several places and plug that in. Let's go here. The area is 5 plus 2. 25 over 5 is 5 plus 2. So the area when x is 5 is 49. So the smallest area, the lowest value we get for area is 49. So the minimum area is 49 square inches. That occurs when x is 5 inches and y is 25 over x, so 25 over 5. So that's also 5 inches. Notice that will give us, if that's 5 and that's 5, that'll give us 25 square inches. And that makes for the smallest sheet of paper possible. So that's just another example of optimization. We took a scenario. There are lots of ways that we could make a sheet with the required characteristics. We could have made 25 square inches here with 1-inch margins, but that might not have been the largest or the smallest possible. So to get the smallest possible, we needed these dimensions. Now the next section, 11.8, is another application of derivatives. This is called Newton's method. What Newton's method does is help us to approximate zeros of a function. Let's suppose we have a function. Suppose it does something like this. Then the way this works is this function has several zeros. If we have a graph, we can look at them, we can figure out what they are, but if we're just given the function, that'd be less obvious. So let's suppose we make an initial guess. Let's suppose we guess this value And if we plug that into our function, we would get this y value, which we can see that's not is going to be 0. So that's not the x-intercept. But then what we can do, let me adjust my curve just a little bit. So this is the y that corresponds to this x. So we can draw a tangent line to our function at that point. Still need a good smooth curve. And then we can use the location of that particular x. It's easy if we know the equation of a line to find the x-intercept for that line. We can use that as our new guess. So if we guess, let's say, this value, we could draw a tangent line to our curve. This one is just not working out so well. It would help if I made a good smooth curve. Let's draw our picture again. In fact, one second. Okay, sorry. I had several things going on today. So let's try this drawing again. So let's suppose this is our initial guess for what would make our function 0. Don't know what the graph looks like. We're just told, hey, this is our function. We're going to pick some number, plug into our function, and see how close to 0 we get. So if it doesn't make 0, that's not a huge deal. We can consider the actual y value. And one thing we can do is we can find a tangent line. We spent a while finding tangent lines. So let's draw a line tangent to our graph at that point. And if we have the equation of a line, it's pretty easy to find out what makes that intersect the x-axis. Keep in mind, at an x-intercept, the y value is 0, so we could let y be 0 and solve for that x pretty easily. Then we could let that be our next guess. So we could find the actual y value, draw a tangent line at that point, and notice the tangent line to our graph at that point, that's really close to what the actual x-intercept is. Even if we weren't extremely close, we could keep going through this process until we got a value so that when we plugged it in, it gave us really close to 0. So let's see how we're going to get these numbers. Let's erase some things and go through our notation, try to generate a system. So let's call our initial guess x of 1. So at this point, the x value is x of 1, the y value is f of x of 1. Also, if we can take the derivative of our function, then the slope of this line is our derivative evaluated at x of 1. So remember, if we know a point and a slope, we can come up with the equation of a line. Y minus the y coordinate equals the slope times x minus the x coordinate. So this is the equation of our tangent line. Now, in order to find out where that tangent line intersects the x-axis, we can let the y value be 0 And let's call that new x value x sub 2. So let y be 0 and solve for x sub 2. So if y is 0, we just have a minus f of x sub 1. Let's get rid of the f prime on the right by dividing both sides by f prime. So those cancel. So x sub 2 minus x sub 1 is this ratio. So if we want to know x sub 2, add x sub 1 to both sides. So our new x value is our old x value minus this ratio. So then if we used that x value, x sub 2, and the corresponding y value, we could draw a tangent line. And the slope of that tangent line would be f prime of x sub 2. So y minus our y value equals our slope times x minus our x value. That'll give us the equation of our second tangent line. So where that second tangent line intersects the x-axis, we could call that x sub 3. So if we solved, x sub 3 would be x sub 2 minus f of x sub 2 over f prime of x sub 2. So notice, if we have an initial value and subtract the ratio of the function at that value over the slope of that value, that gives us a new approximation. So we have an initial guess. We basically come up with a linear function that approximates our regular function and find its 0. So this is our new approximation. Then for that x value, we get a linear approximation that generates a third potential 0. And we keep going through this algorithm until we have the level of precision. So you'll often see this x sub n minus f of x sub n over f prime of x sub n gives you x sub n plus 1. If we have one value and do this, that gives us the next one. We have one value, do this, it gives us the next one. So if this was 4, it would give us the 5th one. If this was 7, it would give us the 8th one. So let's work out a Suppose we have some function, x squared minus 3, and we want to determine a 0 of this function. What is some number that makes our function 0? Now, we could solve that numerically. Add 3 to both sides, or I say numerically, algebraically. So the values are plus or minus the square root of 3. Some things are not as direct to solve. If we had some function and we set it equal to 0, we probably don't know how to factor that. That's not quadratic, so we can't use square root principle, quadratic formula. So we would need some technique to find what are some things that would make that equal to 0. What are some x-intercepts? So technically, when we find zeros for this, they're going to be represent the square root of 3. So we're going to make a table. We're going to make a table that is our x values, f of each of those values, our function at those values, our first derivative at those values, the ratio of our function divided by our derivatives, and then our x minus that ratio, which is our new value. Let's continue until we achieve a precision of 0.01. That means basically until our x value, our c, is within 0.01 of the actual value. So let's see how we can do that. Let's suppose we make an initial guess of 2. Now if we substitute 2 into our function, 2 squared is 4 minus 3 is 1. We also need our derivative. Our derivative is 2x. So if we substitute our x value into our derivative, we get 4. F divided by f prime, 1 divided by 4 is 0.25. So if we take our x minus the ratio, we get 1.75. So that's what our algorithm approximates to be the 0 of our function. So we made an initial guess of 2. We ran it through and our algorithm said, well, that's pretty close, but 1.75 is better. So then we're going to take 1.75 and see if our algorithm, what it gives us, because it'll probably be closer. So if we do 1.75 squared minus 3, we get 0.0625 for our function. If we put 1.75 into our derivative, we get 3.5. And if we divide those, 0.01, let's go to 4 decimal places, 0.0179. So if we take our x minus that ratio, we get 1.7321. So to 1 decimal place, that's the same as what we had. We want to be the same to the hundredths place within 2 iterations. Notice they're within 2/100ths of each other, but we want them to be within 1/100th of each other. So let's just keep going until 2 successive x values have the same value to 2 decimal places. So we're going to start with 1.7321. We're going to plug that into our function, 0.00017. Then we're going to substitute that into our derivative. So 2 times 1.7321, 3.4642. Take the ratio, 0.00017 divided by 3.4642. That's really small. That's 0.00049. 1, 2, 3, 4, 5, yeah. 4.9 times 10 to the negative 5. So if we do our 1.7321 minus 0.00049, 1.732. If we round it to the next place, 1. So notice this one, even to 4 decimal places, these are basically the same. So this 1.73, if we're wanting to go to the nearest hundredth, we have the same value to the hundredths. So that's an approximation of what would make our function 0. Of course, if we plug 1.73 in, we don't get exactly 0. If we plug that into our function, we don't get exactly 0, but we get close. So that's close to what actually makes the function 0. Now, when we algebraically solved for x, we said that's the square root of 3. Notice if our calculator takes the square root of 3, we get 1.73, and then some more decimal places. So really, we use Newton's method to approximate the square root of 3. If we wanted to approximate the square root of 5, if we wanted to find out what is the square root of 5, and we didn't have a calculator to do that, let's see how we could do that. Let's get rid of the radical. So we got rid of the radical. Let's subtract 5 from both sides. Now let's suppose we have some function called x squared minus 5. If we find out what makes that function equal 0, we will be finding the square root of 5. Notice that's why we got a 0 over here, because Newton's method is designed to find what makes something equal to 0. So we could, if we set this equal to 0, we can say this is our function. We're finding out what makes that equal to 0. The reason we squared both sides is so that our polynomial we ended up with didn't have a square root in it. We could technically get this equal to 0, or get a 0 on one side, and we could say, well, our function is x minus the square root of 5. Find out what makes our function 0, and that answer would be the square root of 5. But if we don't have a calculator, if we don't know the square root of 5, how are we going to do this? How are we going to take a number minus the square root of 5 and get a decimal approximation? This, we can do everything needed in Newton's method without a calculator. We wouldn't necessarily want to, but all that we would do would be taking a derivative, adding, subtracting, multiplying, dividing. We would need our derivative, which is 2x. So when we made an initial guess, we would plug it in. We can square any number by hand, just multiply it times itself. And we can subtract 5 from any number. When we do f divided by f prime, that's something you can do by hand. You wouldn't necessarily want to, but you could. So we could do this entire situation without even having to use a calculator.